Cara. E já está no máximo o som. Hi, good morning. Are you already there?
Yes. Yes.
Hey,
Do you hear me?
Yes, we can hear you perfectly. We are just going to wait like 3 to 4 minutes, okay, before we start, because we are
okay. Waiting. My main problem is that it doesn't proceed to slide numbers to the next slide. Is it normal?
No, I don't think so.
So I will stop share and reshare again.
And share again.
Okay.
Okay.
Yes. Okay, now it's better for me.
Okay, can you put in slide presentation in slide mode presentation, because we can see all your slides now. Or if you are using 2 screens, you should share screen. You should share the screen with the presentation view.
On display, perhaps display. Swap presenter.
Yeah, there.
Okay.
Okay. So
yes.
Does it change now the slides?
Yes.
Okay, perfect. I'm just going to wait a few more minutes so everyone returns to the room, okay? And then we can start.
Yes, no problem, no problem. I will main mute, okay?
Okay. Estamos quase todos, não já? Okay. So, good morning, everyone. Today it's my pleasure to introduce Professor Agapios. I hope that I said this correctly. Sorry. From the University of Cyprus. He's a specialist on VOCs analysis, and we use this technology to map and identify chemical signatures of human presence, to study the indoor and outdoor air quality, as well as to use them as early stage diagnosis for human metabolic diseases. He's also using this for aroma analysis of food items and beverages. And today he's going to talk us about the use of thermal desorption for water box analysis. So Professor Agapiou can start whenever you like.
Yes, thank you, Rita, for the introduction. I will start my presentation. I have the same problem.
You have the same problem again? It's okay.
Okay. I will outline first my presentation. I will introduce you to volatile organic compounds. This is abbreviation for VOCs and their role in taste and odor. I will proceed with the solid phase microextraction analysis, then the thermal desorption analysis. I will continue with the enhanced sorping extraction techniques, and I will end up my presentation with some applications. Now, the air we breathe, it mainly consists of nitrogen, of oxygen, and carbon dioxide. However, there is a small percentage of volatile organic compounds. If these are derived from the biogenic emissions, we call them biogenic VOCs. Otherwise, a number of VOCs that are produced from the human activities are called anthropogenic VOCs or exogenic VOCs. Every day, we smell and taste these VOCs drinking our coffee. At the same time, all biological systems produce volatile organic compounds as well as humans. And of course, they have a strong effect on the climate change. If somebody wants to give a definition to these VOCs, these are called low molecular weight substances with relatively high pressure and low water solubility and polarity. Now, since we are living in the chemistry, this is the world of petroleum, VOCs are everywhere. Thousands of goods contain chemicals linked to serious health problems. Very early, in 1980, scientists identified that the sick building syndrome, saying that the indoor air is more polluted compared to the atmospheric air. Now, why you are studying these VOCs? Because they are, even they are small, they have an enormous potential. First of all, they can be found in many foods and beverages. It is the basic substance that changes and differs by origin, type, or handling. Some organoleptic properties are the results of these VOCs. We can monitor our nutritional effects through monitoring the VOCs. And last, they are considered part of the omics cascade, and thus nowadays there are a lot of applications in the bioanalytical area studying the VOCs for cancer, for early diagnosis of cancer, diabetes, and other metabolic disorders. Since many VOCs are toxic or are known as human carcinogens, they are contaminating the water, so there are a lot of human health concerns. Therefore, we all know that the last years there are a lot of regulations, both in the United States and Europe, as we can see in these slides, indicating that we have to monitor these VOCs, especially in water, mostly with gas chromatography, flame ionization detector, or with GC mass spectrometry. And some years ago, around 30 years ago, there was quite popular the idea of Persian trap and GCMS. However, the last years, and especially due to the development of solid phase microextraction by Professor Paolisi in 1990, there was the introduction of solid phase microextraction in the analysis of VOCs. If somebody wants to change something, if this is a GCMS, so if we want to move to the gas analysis, then we have to change our configuration in the inlet And we have to add actually this merely microseal along with this septum, as well as to change the liner in order to be able to monitor the volatile organic compounds. Now, what is the solid phase microextraction? Is a fast and solvent-less sample extraction technique. It can be used in every matrix. You have to establish an equilibrium between the matrix and the fiber. And there are two options, the headspace analysis or the direct immersion analysis. Nowadays, there are a lot of configurations and different fiber cuttings, as it can see, and as somebody can see in this slide. Now, how it works? You put your sample in a vial. You close the vial. You pierce the septum in the GC using this holder. Then you expose the fire for a certain time, which is called the equilibrium time, and is very important. Then you redraw back your holder in order to safeguard the fiber, which is then transferred to the inlet of the GC, where it's being exposed, and due to the high temperature and the helium, it's passed through the gas chromatography and then to the mass spectrometry. However, these fibers are equilibrium affected, so the results that you are getting is actually a configuration of the sorbent material that you have chosen, the temperature that you use in your sample, and the time, as well as if you are using stirring or agitation, the salting, the pH, and the temperature of your sample. So SPME can be combined with gas chromatography mass spectrometry and is considered an attractive alternative for the determination of VOCs in water. As we can see, an important step is, the most important step is perhaps the equilibrium between the sample and the headspace air in your vial. And then when this measurement is finished, then you move to your GC inlet, where you expose again the fiber in order the VOCs to be desorbed in the GCMS system. Now, if somebody wants to compare the solid phase microextraction with the liquid-liquid extraction or the solid phase extraction, it's obvious that there are a lot of advantages. At the same time, if somebody wants to see the precision, the expenses, the time, the solvents, and the simplicity, then SPME seems to be one of the best options to do for the respective analysis. Of course, there are a lot of disadvantages. Here we can see some fibers that they were destroyed during the insert on the GC inlet. The results that you get are based on are affected by the property of the fiber that you choose. There is matrix affinity, and of course, as Professor Paolizzi mentioned in this review paper, there are around 14 parameters that can affect your final analysis. Among them is the fiber coating, the extraction time, the agitation, the volume that you have in your vial, the pH, the ionic strength, and so on. So somebody must to optimize the processing in order to get as more VOCs as possible. Some years later, in the market, we came up with the SPME arrow. Here we can see the SPME fiber, whereas here is the SPME arrow, which is a more strong and more solid, let's say, kind of fiber. It was introduced by Gerstel. And if you want to use this arrow, this SPME arrow, you need to change again your inlet. You have to put a bigger and GC turned top assembly, as well as a bigger liner, because the configuration of the arrow is much more strong and bigger compared to the SPME. Of course, as you can see here, the sensitivity of the arrow is better compared to the SPME fiber. Of course, what actually changed is that with SPME, we had 0.6 microliters of absorption phase, whereas with SPME arrow, we moved to around 50.3 microliters absorption phase. Now let's move to thermal desorption. I will make some introduction for people that are not familiar with this device. Thermal desorption is a versatile pre-concentration technique for the gas chromatography that it has been used to analyze the VOCs and semi-VOCs components. Now, how it works, I will try to explain you how it works. It's actually based on the absorption of sorbent tubes, and then through a two-stage desorption process, VOCs are desorbed to the gas chromatography and then to the mass spectrometry. So first, you have this pump, so you can pump your sample, your air sample, because initially it was developed for air sampling. This is a pump, this is the tube. You pump the air in the room, let's say, for example, and then you close your sorbent tube, you come back in the lab, and then you expose it, and through the carrier gas, the tube is moved due to the heating, and the carrier gas is moved in a cold trap, where it's actually cooled and stay here for some minutes. Prior, it's been desorbed again in the GC column, and this is why it's called a two-stage desorption process. I will explain this in the next slide with more information. So it can be used either for sampling of solids, liquids, and gases. It's considered again as the SPME and the SPME arrow and environmental friendly solvent extraction technique. It can be automated, and it's been validated under the APA TO17. Now, this is an in-house made thermal desorption that we created back in when I was doing my PhD in the National University of Athens. And I will try now through this in-house made device to explain you the three components of thermal desorption. We start with the sampling, as I told you earlier. You sample the air through a pump, then you can just diffuse. You put the sampling diffusion logs, and you place it in your pocket as a pen, and leave it to suck the air by diffusion. So there is the alternative of sampling either through pump or not. Now let's see how it works. We took our sample, we come back to our lab. So we open this sorbent tube and put it on the opposite position that we did our sampling. Imagine that your sorbent tube is placed in this system here, in this point. This point is called thermal desorption. So there is a block here. You raise up the temperature, and based on the boiling point of the components of the VOCs, these are desorbed and come to step 2. Here in this area, you have this cryo trap. At that time, we used to cool it with liquid nitrogen. Now there is a Peltier for doing this job. So every component, while this block is desorbing the VOCs, are trapped in this cold trap and are staying here for some time until the step 1 is finished. Then very rapidly, we flash the components from the cryo trap to the third block, which is called the connection block, in order to introduce to the gas chromatography. So here on the left, we can see how it works. There is some literature towards this. I'm not going to go in details. What we have to have in mind is that there is this three-step approach. There is the collection, then the desorption, the cryotrapping, and then the cryotrapping desorption. Now, if somebody wants to see a real instrument, what is this cryotrap nowadays in a real instrument? This is the point where it is situated, and in a commercial system is this white thing here, which is now electrically cooled by a Peltier component. And here, this is how a commercial system is now seen. Here is the thermal desorption unit. And here is a configuration that we have in our lab. This here is the GC. This is the EMA, the mass spectrometry here. And here we have the thermal desorption unit. So we sample and put our sorbent tubes here in this system here, where they are desorbed through this, let's say, heating snake, and then they are entering the GC column here, where they are being separated prior to be analyzed and detected in the mass spectrometry system. Now, comparing the sorbent tubes with SPME, it's obvious that the sorbent capacity of the sorbent tubes is much more. So we are achieving much more sensitivity, and there is no need for equilibrium. We can achieve field sampling. So there are a lot of advantages compared to the solid phase microextraction analysis. Of course, both SPME and thermal desorption are based on desorption, is a kind of desorption technique. Now, there was this need for higher capacity sorptive extraction tools, and therefore companies like Gerstel develop these coated steel bars, or these films here that are placed in the vials. And if we can see here what is changed with these commercial systems, this is the SPME fiber, this is the twister by Gerstel, and this is this thin film SPME component, is both the surface area and the volume of the sorption phase. And if we can see here in this chromatograms, we can see here is the SPME in analysis of wine, aroma analysis of wine. And when you are using this thin film SPME, the components are getting wider and more obvious. And of course, we have to take into consideration that both all these equilibrium-based techniques are based on the octanol water coefficient. Now, the last years, let's say 3-4 years, having this in mind, the owners of this, the company that owns these thermal desorptions, move and prepare and provided in the market these high capacity sorbing extraction tools, which is shown here. They are named, its name is HiSorb, and it's provided by Marks International from United Kingdom. Here we have 65 microliter sorption phase volume. So you have to, in the beginning, there was only PDMS available in the market, and last summer, they provided us with new HiSorb multiple phases like the SPME. And so how it works, it's the same as the SPME. You put, this is an olive oil sample. You put your sample in a vial, you close it, and then you pierce the septum, you insert this HiSorb after the equilibrium is reached, and then is redrawn back, and you put it on an empty sorbent tube. So having this HiSorb probe in an empty tube is being desorbed, And again, it takes it follows the same procedure as exactly in the thermal desorption. By this, thermal desorption is now became a technique that can accept a passive absorption extraction probe called HISORB. Here, I will show you some of our results, not in water, but in let's say, similar applications. Here we can see the analysis of gold wastewater after an electrooxidation. As you can see, here is the raw sample, and with color is the 2 hours after the electrooxidation. It's obvious that we were able to identify a lot of aldehydes, acids, and so on. And if we zoom in this chromatogram, we can see that we were able also to identify a lot of chlorinated compounds that are due to the chlorination of water. Now, if we move to a more if we continue our results with treating the same sample with electrocoagulation, again we can see that HISORB was able to identify a lot of VOCs, both in the raw sample as well as in the treated sample after the electrocoagulation. If we move and see how it performs in a more complex system, such as that of oil, virgin oil, we can see that the results are very nice. We can see again that with HISORB, we were able to identify a lot of VOCs that are responsible for the aroma profile of extra virgin oil. Now in our lab, we are trying to develop a dynamic headspace system. Here is the results of milk that we use with HISORB, here with SPME, and here with this dynamic system. We actually purge our sample with nitrogen and then move the headspace VOCs to a serpent tube, where at the end there was this pump. If we can see here how it works, there is this carrier gas. It moves, it pushes actually these VOCs to an absorbent material, which is then placed in the thermal desorption block and is being desorpted in the GC MS. If you want to clean your system, then you just purge it again with nitrogen. Now, if we want to be more to compare the dynamic headspace sampling with the other techniques such as the SPME, it's again a game of volatility. And what are the advantages now? The advantages are that there is this effective and rich stamp. The extraction time is much shorter compared to the SPME. The DHS, dynamic sampling, remains a valid and effective green technique next to the HISORB in order to use your thermal desorption for the analysis of VOCs. Concluding, thermal desorption-GC appears to be the golden choice, and it offers the advantages of lower limit of detection, off-field sampling, sensitivity, easy to use, and automatization. Prior thanking you, I would like to inform you that these are the main activities of my group. We are focused on biomedical applications, environmental monitoring, food and beverages analysis, and of course, waste and fuels analysis. Here is the current projects we are running. We've moved to aroma analysis of wine analysis, olive oil analysis, as well as electronic cigarette. And of course, here is the lab. Our lab is situated here in the University of Cyprus at the Department of Chemistry. And as mentioned to Dr. Karaogia, there is always the opportunity of short-time scientific mission from somebody that wants to come and stay here and test our thermal desorption system. Thank you for your time, and if there are any questions, I will be glad to answer them. Thank you.
Thank you so much. Thank you very much for your insightful presentation. Is there any questions? No questions? I have a couple of questions. I'm just going to stick probably to one or two. So first, and it has nothing to do with water, but to analyze urine samples, how do you need the samples to be preserved?
Yes.
Could you listen to me?
Yes, I'm listening, yes.
Okay, so I would like to know, to analyze urine samples, can the samples be preserved at -20, for example? Or you need the samples to be preserved after collection at -80?
I will prefer -80. For example, in this way, wastewater analysis that we perform, we were measuring the carbon oxygen demand, the COD, and we noticed that in -20 we had a lot of changes. So that is why when we are using biological fluids, the most advisable temperature is that of -80.
Okay, thank you. Is there any question? Okay, I think there is one question here. Rita, I'm having troubles with your Mac. I'm a PC girl, so can you see the chat room?
Yes.
So is there a thermal desorption device automatized, or do you need to analyze samples one by one?
No, there is for many years now automation in thermal desorption. To be honest, there is this PAL system and the Sentry system both from Marx and I think Gerstel. And you can analyze at the same time both you can do thermal desorption analysis of desorbent tubes. With the same automatic sampler, you can do high sorp analysis, SPME analysis, and so on. So indeed, there are automatic systems, robotic systems, but of course, their cost is too high. It's around 40 to 50,000 euros.
50,000?
Yes.
Okay. Yeah, it's a high cost. And I have one more question, if you don't mind.
Yes, please.
Can you use this technique for semi-volatile organic compounds, for VOCs?
Yes. This is what we do here in this picture. Whereas one student that is one of my master students is sampling air from hair salons, and we are able to identify even phthalates, which
That's
are not.
I was asking just about phthalates, about the drinking water.
Yes. Everything depends on the sorbent material, and one of these sorbent material quite known is Tinax. Of course, there are much more in the market, around 5 or 6 choices, and based on your application, you can you can order them, and indeed they can identify even semi VOCs because you can desorb them at of course. You have high sorping capacity, but at the same time, you can raise your temperature up to 300, 350 in order to desorb them. Where are the boiling points of the semi VOCs?
Okay, that's perfect. Thank you so much. If there are no more questions, Rita, we can move to the next presenter. Okay, thank you so much.
Okay, thank you. Bye-bye.